Greetings, Mr. Sutton here with the BC Calculus 8.2 Part 2 homework solutions on arc length. On this problem, I need to set up an integral and find the length of this curve without a calculator. Since I have an x equals y sort of situation, I'm going to use this formula where I have the integral from a to b square root of 1 plus dx over dy squared dy. So I need the derivative of this thing with respect to y. Now the good news is, since it's already an integral, I can just use my fundamental theorem and basically just plug y in for all the t's here. I'd multiply by the derivative of y, but that's just 1, so we don't have to worry about it. So I've got the square root, so actually integral from negative pi over 4 to positive pi over 4. Let's get our limits of integration there. And now we have the square root of 1 plus, and now this is all inside of squared parentheses, the square root of secant fourth y minus 1. So the good news, although I have two levels of square roots, this inner square root is going away because I'm squaring all that. So this is 1 plus secant fourth y minus 1. And I can cancel out those 1s. So this is really just the square root of secant the fourth of y. And let's see, so let's cancel out those 1s. What is the secant fourth square rooted? Well, that's just secant squared of y. And now the antiderivative of secant squared is tangent. Evaluating tangent from pi over 4 and negative pi over 4, we have tan of pi over 4 minus tan of negative pi over 4. At this point, you've got it down to, these are all considered constants, so you could actually stop here if it's a free response. But if you wanted to keep going, tan of pi over 4 is 1. Tan of negative pi over 4 is negative 1, but we're subtracting that, so you really have 1 plus 1. And then, yeah, that's 2. On this problem, I'm trying to find the length of the path described by this set of parametric equations from 0 to pi. Since I've got parametric equations, on this no calculator question, I'm going to start with my formula for parametric length. That's the integral from a to b square root of dx over dt squared and dy over dt squared. So dx over dt, that's the derivative of this x equation here. I'm going to need the chain rule on that. So I've got sine of something, derivative of that is going to be cosine of the something, cosine of t to the third. And in general, I have the integral from 0 to pi here. So now we have a square root. And in here we have cosine of t cubed times the tail. So this is going to be times 3t squared. And that's all being squared. This whole thing is dx over t squared right here. Next, I need dy over dt squared. dy over dt is going to be the derivative of e to the 5t. Just using a quick chain rule, that's going to be 5e to the 5t. And we're squaring that. But now that doesn't match any of the answer choices, not exactly, so we have to simplify it at least a little bit. We don't have to evaluate it all the way, but we have to simplify it enough to match. So let's see here. This is going to be a 9t, or yeah, it's going to be a 9t to the fourth times cosine squared of t cubed. And then over here, this is going to be squaring the 5 and the e, 25 e to the, let's see, we're multiplying exponents, so 10t. And that is going to match which answer choice? Well, that looks like answer choice C. For this no calculator problem, we want the length of the graph from y equals tan of x between x equals a and x equals b. And they're telling us that 0 is less than a is less than b is less than pi over 2. So you might be wondering why they're giving us this last piece here. The reason is that what we're about to use with our arc length formula assumes that we don't have any discontinuities. We're assuming that we have a smooth curve where the curve and its derivative are both continuous. So this whole pi over 2 business, remember, tan has a vertical asymptote at pi over 2. So we're saying that all of this happens before we get to that trouble spot. So we can use our formula. So our formula then that we're going to use, since I've got a function that's in terms of x, I'm going to use the integral from a to b of square root of 1 plus dy over dx squared, dx, this one here. So to use this formula, first I need limits of integration, which also are a and b on this problem, which is kind of interesting. For dy over dx, I need the derivative of tan of x, which is secant squared of x. And now that is actually being squared itself, so the secant squared is being squared. And that doesn't quite match anything I have here, but if I square this secant squared, I have, let's see, 1 plus secant fourth power of x. And now that's going to match, let's see, answer choice E. For this one, the length of a curve from 1 to 4 on x values is given by this integral here. So they're already giving us the arc length. If the curve contains the point 1, 6, which could be the equation of the curve? So this is where you have to look at the general format and kind of know what the arc length formula looks like. If we're going with a function in terms of x, your arc length formula is integral from a to b of square root of 1 plus dy over dx squared dx. So we're basically asking what the original y function was. And we have to realize that based off of this format here, this 9x to the fourth is really dy over dx squared. That means that dy over dx itself is what you get if you square root 9x to the fourth, which is 3x squared. So this is our differential equation. We essentially have to solve this differential equation with an initial value of 1, 6. So just remembering back to our diff-EQ, we need to take the antiderivative of both sides, and we quickly check to see if we need to separate the variables, but we don't. There's no output variables over here. There's no y over here, so we're good to go. So taking the antiderivative of 3x squared, that'll give us, let's see, and we have to take the antiderivative of the left too. That gives us just y on the left. So this is going to give us, let's see, the exponent bumps up to a 3. Divide by that, we have x cubed plus c. Plugging in our initial value, we can write 6, the y value, equals 1 cubed plus c. And then that means that c must have a value of 5 if we subtract that 1. So plugging that back in, we have x cubed plus 5. And that's going to end up being, let's see, 5 plus x cubed. That's choice B. On this problem, we want the length of ln of x from 1 to 2. Since I have a y equals x kind of situation, I use this formula here, where we have square root of 1 plus dy over dx squared. So I need the derivative of ln of x, and I'm taking an integral in general from 1 to 2. So we're going to have the square root of 1 plus, now the derivative of ln of x, that's going to be 1 over x, and we're squaring that. So that's going to be 1 over x squared inside there. And now let's carefully see if we can match an answer choice. So look, this is going to look like choice A. B is pretty close, but we're missing the square root, so choice A it is. For this problem, we want the length of the curve with the parametric equations x equals t squared and y equals t from t0 to t4. So we're going to use our general parametric length function, or formula. That's the integral from a to b of square root of, and we have basically dx over t squared plus dy over dt squared. So dx over dt, that's going to be, and hold on a sec, we have the integral from 0 to 4. There we go. All right, so now our derivatives, we have dx over dt, that's just going to be 2t, and we're squaring that inside a square root. Derivative of y, that's going to just be 1, and again, we're squaring that. Not that it really matters because it's 1. Let's simplify this a little bit to match one of the answer choices. 2t squared, we're squaring the 2 and the t. This is the place where a lot of people are going to mess this up. So that's actually 4t squared plus the 1 that's already there. So that's going to end up giving us, let's see here, choice D. Is that the, yep, that's an exact match. E is close, but we have this random 2 pi out here. So choice D. For this one, we're trying to find the length of radical x over the interval 1 to 4. And I'm doing this without a calculator. I just have to match one of these answer choices. So my general formula then that I'll start with, we have integral from a to b square root of 1 plus dy over dx squared dx. So I have the integral from 1 to 4. And now I have the square root of 1 plus, and now the derivative of the square root. This is initially x to the 1/2, so we can write 1/2 x to the negative 1/2 inside that squared parentheses there. Now I have to match one of these answer choices. So if I square this stuff here, I've got 1/4, and this is x to the negative 1 if we multiply the exponents. Well, 1/4 times x to the negative 1, that's really 1 over 4 times x in the denominator. And that is going to match, let's see, just matching these carefully here. We have a 1 plus 1 over 4x. That matches answer choice D. C was pretty close, but we were subtracting, so be very close with this last step. For this one, I'm trying to find the length of the path described by this set of parametric equations from time 0 to 1. Since I'm going parametric here, I'll use the formula integral from a to b of square root of dx over dt squared plus dy over dt squared. So I have the integral in this case from 0 to 1. And now inside my square root, the derivative of x, that's going to be, using our power rule, this cancel, the 3 and the 1/3 cancel, so you just have t squared. But be careful because we're already squaring that inside the square root. Next, for dy over dt, 2 times 1/2 cancels, you just have t, but again, you're squaring that. And just to clean this up a little bit, we then have the square root of t to the 4th plus t squared. So that's going to match answer choice, is that C? Yep. On this problem, we've got this graph of f that's differentiable over the period from 0 to 10. And let's see, we have some areas given. They said from 0 to 5, this area is 10. From 5 to 10, the area is 27. And they also gave us the arc length. From 0 to 5 was 11, and then the arc length from 5 to 10, this arc length here was 18. And we're also told we have 2 critical points at 3 and 8. Cool. We want to find the average value now of f on the interval from 0 to 5. So average value, we're going to have 1 over the interval length, so that's going to be 1 over 5 minus 0, times the integral from 0 to 5 of whatever you're trying to average, so the f of x function in this case, f of x dx. Okay, well, this is really going to be 1 over 5 times, now we need to know the area under the f curve between 0 and 5. Now, they gave us that in the graph. In the problem, they said the area of the region enclosed between the graph of f and the x-axis between 0 and 5 is 10. So that's this area here. So we're going to call this, because it's under the x-axis, we'll call this negative 10. And then you could leave it that way, or you could multiply this out to get negative 2. On this problem part, they want us to evaluate the integral from 0 to 10 of all this stuff here, and then show our computations. So we're going to use some integral rules to kind of split this up. I can split this into 2 integrals. In the first integral, I have the integral from 0 to 10 of 3 f of x, and I can pull that 3 out to be kind of a constant multiplier outside the integral if I want to. In the second integral, now we're adding these together, we have the integral from 0 to 10 of just 2 dx. All right, let's take these one at a time. So integral from 0 to 10 of f of x, that's the area under the f curve with the negatives factored in here. We already saw in part A that the area from 0 to 5 was going to be 10, but it's negative 10, right, because this is under the x-axis. So we have 3, parentheses, negative 10. And now we also have the area from 5 to 10, which they told us right here is 27. So we're going to be adding 27 in there. Over here now, we have the integral from 0 to 10 of 2. Well, this is just really a rectangle with a base of, let's see, this is 10 and a height of 2. 10 times 2 is going to give me 20. And you could leave it like this because it's all constants, or we can add it up. This is 3 times 17, that's 51, plus 20 is 71. For this problem, they're telling us g of x is the integral from 5 to x of f of t dt. They want to know where g is concave up and decreasing. So the key on this is we need to know about the first and second derivatives of g, and then use that to figure this out. Well, in order to figure that out, we need to kind of find a connection between g and f, because we already know a whole bunch about the graph of f. So if I take the derivative of both sides here, using my fundamental theorem, I see that g prime of x is really the same as f of x. Okay, so the first derivative of g then matches whatever the f graph is doing, And we want to know about where this graph of g is decreasing. That's the part that the first derivative explains. So decreasing, we're looking for where g prime is negative. I see on the graph here that f, which is really the same as g prime, is negative on the interval from 0 to 5. We're below the x-axis there. That means that g itself is decreasing on the interval from 0 to 5. Now we need to know about concavity, specifically where we are concave up. So I notice that g prime, which again is the same as f, is increasing on the interval from, let's see, this is 3 to 8. And we know we're increasing there because they said that the f graph had critical values at 3 and 8. So we know those are the exact x values of those turnarounds. Since g prime is increasing on this interval, that means that the original g function must be concave up on that interval. Because if g prime is increasing, g double prime is positive, which again means concave up. So putting this all together, we're decreasing from 0 to 5, but we're only concave up from 3 to 8. So to be both concave up and decreasing, we need to start at 3 and go to 5. That's the only region that has both properties. So we're concave up and decreasing then for g on 3 to 5. For this last final boss battle part of this question here, they're defining the function h as 2 times f of x over 2. And they're telling us that the derivative of h prime, is given by f prime of x over 2. Which is nice of us, nice of them. We could have figured that out on our own. I mean, this is just the derivative of f times a tail of 1/2, which would cancel out that 2. But, okay, they're giving it to us. So they want us to find the arc length of h from 0 to 20. In general, arc length of h, since this is a function in terms of x, we're going to have the integral from a to b of square root of 1 plus dy over dx squared dx. So in this case, we have the integral from 0 to 20 of square root of 1 plus h prime of x squared dx. And they actually told us h prime was f prime of x over 2, which again is very nice of them. So we've got f prime of x over 2 inside here. That's the only change from this step to this step. But now, how do I figure this out? I have some information about the arc length of f right here, this graph, which is essentially what this is kind of sort of talking about. But this is talking about the arc length of f of x over 2, not f of x. So we can't quite use this graph as much as we'd like to in order to answer this question. So for that reason, I'm going to do a little substitution so that I can get all of this integral with an f prime of, well, not x over 2 in here. We want to end up with like f prime of a single variable in here. So to do that, I'm going to let u equal x over 2. I'm going to use a little substitution. du is going to be 1/2 dx. So dx over 2, which means du is going to be 2 du, or dx is going to be 2 du. There we go. Substituting back in. Oh, wait, I need u values as well. So using this u substitution, if x equals 0, u is going to be 0 over 2, which is also 0. If x equals 20, then u is going to be half of that, 10. Putting it back together, I now have the integral from 0 to 10, and I have the square root of 1 plus f prime of u squared. And I need a du over here instead of a dx. But that means that I've got 2 du to make that substitution. I'm just going to take the 2 that I would put here and just bring it outside the integral so I don't have to mess around with it. And now, in order to solve this problem, I basically need to find the arc length of the f function on the interval from 0 to 10 and then multiply all that by 2. Well, here's the good news. They told us the arc length of f from 0 to 5 and then from 5 to 10. So from 0 to 5, they said the arc length was 11. So I've got 2 times 11, and I'll put this in a parentheses here. But to get the full arc length from 0 to 10, we also need to know about 5 to 10. So the arc length from 5 to 10, they said, was 18, so we'll add 18 in there. And this is numerically equivalent to the answer, or you could add this up. This is 2 times 29, which is 58.